Our fifth look at what is a patient recognizes that every patient is a life history that unfolds from egg through fertilization, birth, growth, maturation, reproduction, and on into old age and death. These patient life histories have evolved, and they continue to evolve, and that evolution has both medical causes and medical consequences. Patients are phenotypes. They are traits, not genes. And trait evolution is what's analyzed by life history theory. Life history theory has successfully explained why organisms are small or large, why they mature early or late, why they have few or many offspring, why they have a short or a long life, and why they must grow old and die. So what is it that causes life histories to evolve? Well, at a very, very basic level, they result from the interaction of extrinsic and intrinsic factors, from things in the environment and things in the organism. The extrinsic factors are those that influence age or stage-specific rates of mortality and reproduction. So risk and nutrition and things like that. This is where the environment comes in. Nutrition, disease, violence, medicine, public health, those are all factors that are affecting age and stage-specific rates of mortality and reproduction. The intrinsic factors primarily include trade-offs among traits, and here phylogeny, genetics, development, and physiology are all involved in establishing these critical connections among traits. The analysis done is one of costs and benefits. For example, what are the costs and benefits of maturing earlier or later, of investing more in each of a few children or less in each of more children? Those are standard life history questions, and so you can see the framework is one that conceptualizes organisms as having trade-offs that set up a structure of costs and benefits. The method of analyzing trait evolution that's developed for life history traits suggests how all traits evolve, including traits in the immune system, traits having to do with physiology, and so forth. Those can all be cast into this sort of framework. An example of trait evolution is age and size at maturity. We'll focus just on this one. Natural selection shapes the evolution of age and size at maturity to maximize reproductive success that results from maturation at different ages and sizes. It's a very straightforward approach. How many children and grandchildren are you going to get if you mature at this age and size rather than at some other? That's the question. So let's make a few assumptions about costs and benefits. First, delaying maturity improves offspring survival. So older organisms have higher quality offspring. Delaying maturity improves offspring number. Older organisms have more time to grow, so they're bigger, so they can have more babies. Earlier maturity shortens generation time. That's a benefit. And early maturity shortens the period of risk before reproduction begins. So you're more likely to reproduce because you've survived to reproduce if you can do it faster. So these things are trading off with each other. They're in opposition. There is an equation down here, which probably looks a little formidable. It's the Euler-Lotka equation. It explicitly relates fitness to these traits. Now in this equation, fitness is this thing here, little r. That's the rate at which a variant will grow in the population. And in a stable population, this relationship between age, fecundity, survival, and fitness can be shown to be true. Basically what you do is you are integrating between age at first reproduction and age at last reproduction of reproductive success, that's probability of survival times fertility, weighted by the discount of the population growth rate. And in a stable population, that will equal 1. This gives a way of relating little r, which is fitness in this formulation, to age at maturity, alpha. Let's do that for these curves here. So these curves come out of that equation. Here's age at maturity, alpha, and here's fitness, little r. And what you can see is that under two different sets of assumptions, This is one which is based primarily on an effect on juvenile mortality, and this is one which is based primarily on fecundity. You can see that there is a peak fitness associated with a certain age of maturity. The actual age of maturity is this dashed line here. You can see that the model is bracketing that observed age of maturity. This particular analysis is for the western fence lizard. Now, you can ask yourself, what will happen when a range of environments is encountered? So here we have along the x-axis age, along the y-axis we have weight. These curved lines here are growth curves, so they indicate how weight is varying with age. It's increasing rapidly here with age, with rapid growth, and a little more slowly here with slow growth. Let us suppose that organisms decided that they were always going to mature at the same weight. Well, if they were growing rapidly, they would mature young, and if they were growing slowly, they would mature quite old. And the problem they would encounter is mortality. Let's suppose that they decided, on the other hand, to mature always at the same age. Well, if they mature when they're at this point, when they're growing rapidly, they're big, but at the same age, when they're growing slowly, they're small. So here, the problem is that they lose fecundity. They aren't able to make as many offspring. So just on that very simple ground, one would expect a flexible compromise, something in between. Now, what do human females actually do? They are phenotypically plastic. This is Rose Frisch's data on women in England and Scotland from the 19th century and from Hutterites in Iowa from the 20th century. And the women in England and Scotland in the 19th century were stressed by poor nutrition and hard work. And the women in Iowa in the 20th century were growing better and they weren't as stressed. And basically what you can see here are different measures of this is procreative power on this axis over here. This is age down here. And marked on here are best fitness for procreation. Okay, so this is a shift here of about 4 or 5 years. In other words, in the 20th century, women were able to mature and have children 4 or 5 years earlier than they were in the 19th century, and that is a plastic response. So if you use that framework that you saw with the equation and the example from the lizard, and you ask what is the optimal reaction norm for maturation in humans, it is this blue line here. And if you put in the amounts, the correct estimated parameters for the 19th and the 20th century, this model predicts about 4, 5, 6 year shift in age at maturation, age at first birth. Now, what that means is that when human females grow faster, they mature younger and larger. And this is quite consistent with an optimal evolved reaction norm. Interestingly, there is also on this figure another line. It's this red line. This is the difference made by nurture. This red line indicates what one expects if juvenile mortality rates remain low. There should be a shift of the entire reaction norm down to the left, meaning that women should be maturing slightly earlier and slightly shorter, slightly smaller than they were before juvenile mortality rates dropped. So you can think of this as being selection that is a result of improvements in medicine and public health. We got a surprising confirmation of this when we analyzed women in the Framingham Heart Study. We looked at selection operating on those born between 1890 and 1950, and then projected the change that they would experience over the next 10 generations in height and in age at first birth. Height predicted to decrease by about 2 centimeters, age at first birth by a bit over 5 months. We then contrasted that with rates of evolution in 19 natural populations of plants and animals. This is for height, this is for age at first birth in humans. Here you have intervals over which change was measured. Here you have the rate of change. The scatter of black points gives you all the measurements for plant and animal populations in nature. The humans are sitting right in the middle of them. Humans have normal rates of evolution projected when compared with other organisms. Contemporary humans are still evolving, and they are evolving in the direction that had been predicted by that model of life history evolution. This is what an optimal reaction norm for age and size at maturity looks like for many organisms. The dotted lines are growth lines. The dark line here is the optimal reaction norm. So basically what it is saying is that if you're growing fast, mature, young and large, and if you're growing slow, mature, old and small. There are other possible reaction norms, but this is certainly one that seems to be common. Now, why is there earlier age at first birth in contemporary humans? Well, age and size at maturity are determined by trade-offs between infant mortality and age of mother. The offspring of younger first-time mothers suffer higher mortality rates. That's the trade-off with juvenile mortality. So here is a curve of infant mortality versus age of mother at birth for the population of the U.S. in 1960-61 with a sample size of a bit over 100,000. And you can see that girls who are having offspring before they're 10 years old have a very high probability that their baby will die. That drops down to a minimum at about 22 years of age and then begins to rise particularly strongly after 35. So what's going on when medicine improves early childhood survival is something that has a direct impact on the evolution of age and size at maturity. When modern hygiene and medicine lower infant mortality rates, they reduce the evolutionary costs of earlier maturation, but the benefits of earlier maturation stay the same. So the cost-benefit ratio changes. It's become possible, and it pays off to mature earlier. With the costs of earlier maturation reduced and the benefits unchanged, maturation shifts to earlier ages. The entire reaction norm then moves down and to the left. Similar effects have also been found in other human populations, in particular those that, like the US population, have already moved through the demographic transition, Finland and Australia. So the important points from this lecture are that what evolves is not a fixed value of a trait, but the entire plastic response, the reaction norm. Reaction norms depict the interaction of nature with nurture, of genes with environment, and they are very useful for making the point that all aspects of the phenotype result from gene-environment interactions. The nature-nurture debate is a false debate. Both things are important. Public health measures and medical care have population-level consequences. They change selection pressures and they alter the course of evolution. That's something that most doctors probably don't realize. The Framingham study describes the biology, but at the same time, culture is pushing women in the other direction to have their first child later, particularly in families where both couples are professionals and women want to delay childbearing for professional reasons. The result is increased conflict between biology and culture. So this is not a paradox that women are under selection to have earlier age at maturation in Framingham, Massachusetts. Instead, it is a pointer to the increased intensity of conflict between biology and culture. So to summarize, selection shapes life histories from birth to death. Changes in life history events have costs and benefits, and selection shapes them to maximize the difference between the benefits and the costs. That process is constrained by trade-offs, which connect traits that are genetically, developmentally, and physiologically bound together. When traits are connected by trade-offs, then changes in one trait that improve fitness cause changes in other traits that decrease fitness. We'll see that in greater detail in the next lecture. What evolves is often not a fixed trait, but its plastic response, its norm of reaction. How it is expressed is a function of the environment encountered. So the take-home from this lecture is a patient is not a fixed object developmentally. A patient is a point on a reaction norm that describes all the different possibilities that that genotype had in interacting with various environments.